Hello, everybody. Mr. Hinnon here, and today's lesson is on Chapter 14, Moles and the Ideal Gas Law. So we had a lab activity. So one of the things I definitely want you to continue with is that lab activity on the PhET simulation on the gas laws, and use that to kind of get this ideal gas law that we'll be playing around with this week. And then later this week, we're going to be talking about kinetic theory as well. So I'm kind of putting this in there, but also I really want you to kind of do those gas law labs before you kind of move into this, but that's kind of the beginning of it. So we've talked already a little bit about the mole and Avogadro's number. We did the remember the allamole. We watched the how big is a mole idea. But you can talk about atomic masses here and atomic numbers. So when I look at this and I talk about how there's an atomic number, there's an atomic mass, and we're giving those information to you, the idea is they are telling you a little bit about that particular atom or element. So when I say an atomic mass unit, which is probably the easiest one to do, it's truly saying that if I have one atom of hydrogen, it has a mass of 1.00794 atomic mass units. So that kind of gets at it. Or if I have beryllium here, right there, it's 9.01218 atomic mass units. Now, the atomic mass unit does actually have a mass in kilograms that we can convert. This is on your conversion sheet, so if we wanted to change it into kilograms, we could, but that's the beginning idea of it. But obviously, it takes another step, because if you have 1 mole of a substance, this number down here tells you what its mass is in grams. So they don't actually show this, but if you had carbon 12, for example, it actually has 12 grams for an entire mole of carbon 12. So that's what they're getting at, and that's the idea of Avogadro's number, the 6.022 times 10 to the 23rd atoms per mole. You can kind of write that as an equation here, where you can say the number of moles is actually the number of atoms divided by Avogadro's number, kind of going after it. I usually like to use this idea of the atomic mass and kind of go after it that way. So I don't use this as kind of a separate equation idea, but these are things that we've already talked about and played around with. So when you have the mass per mole or grams per mole of a substance, it has the same numerical value as that atomic mass. So this is actually a very good statement to kind of remember, and that'll allow us to kind of figure all this lovely stuff out. For example, hydrogen, oxygen, lithium, sodium, magnesium, all those different quantities. So here, let's try a little example. The Hope diamond, diamonds are basically just carbon. So if you had a 44.5 carat diamond, how many carbon atoms are in there? That's basically part A. And then if you have the Reeves, the Rosser Reeves ruby, which is 138 carats, and it's aluminum oxide, rubies are aluminum oxide, how many aluminum oxide molecules are in there? Ruby. Well, the first part is we know that 1 carat, or this would something they give to us, 1 carat is equivalent to 0.2 kilograms. So we'd have to change it. I'll use the Hope diamond idea that we'd take this 44.5 carats and we'd have to multiply it by 0.2 grams per carat. That's basically going to change it into grams for us. So I'm going to pull out my hand dandy calculator here. 44.5 times 0.2 is 8.9. So the diamond itself, or the diamond itself is about 8.9 grams for that. Then what we're doing is we're realizing that's grams of carbon, and we're going to try to change this into the number of carbon atoms. So the first thing we're going to do is try to change it into moles. So I know 1 mole of carbon is about 12 grams of carbon. So the grams will cancel out, and I'll change it into moles. So I take my 8.9 divided by 12, and I get 0.7416 repeating. 7416 repeating. Now I'm in moles of carbon. So my last step is I would change this into atoms of carbon. So that's where the 6.02, and I usually just stop at 6.02 times 10 to the 23rd atoms. There you go, into 1 mole. And then we just multiply 6.02 times 10 to the 23rd. And we get our 4.46 times 10, my pin's not writing, 23rd atoms of carbon. So this kind of is where we would change all this stuff and allow us to kind of convert that. So here's an example of that. They kind of do it a little bit differently on the paper, but they end up with the same answer. We can also see that if you've got that aluminum oxide, you've got to figure out the molar mass of it. So they took 2 of their aluminums and 3 of their oxygens and multiplied and added them together. So that's where they got that 101.96. They were using 12.011. That's the exact atomic mass or molar mass of carbon. I was just kind of using a rounded version with 12. Things that you would have those exact numbers using a periodic table or something else, and you'd be good. So that's all that type of stuff. Now, the next step is we want to get into the idea of using gases and ideal gases. So an ideal gas is one that it stays a gas under the conditions we're looking at. So it doesn't change anything about changing to a different state. And we also are looking at low density. So we don't want the molecules themselves to actually collide with each other. So if you notice on here, we talk about the molecules are so far apart, they do not actually interact or collide. And basically it's perfectly elastic. So elastic collisions are happening. It's low density. It's also not going to change into a different state. So all those are going to happen. And when you get into that, you end up with a variety of these gas laws. Slip myself up here for a second. One of them is that we know that pressure and temperature are directly related. So if you increase the temperature of a gas, it's going to increase in pressure. We know this. We have this example. If you've ever tried to heat up a sealed container, it's going to get under high pressure and explode. You're never supposed to take a spray can and put it into heat, because that can happen. If we kind of continue with this, we can also look at pressure and volume. Pressure and volume are inversely related. So what that means is if you keep the temperature the same, you can actually look at how the pressure and the volume are going to change, and it's an inverse relationship. Now this is actually kind of a cool graph over here. What it is what we refer to as a pressure volume graph, but these curves here are what we refer to as isotherms. They're points that have the same temperature. So this is what this particular section of the ideal gas law is telling me, that if I change from this pressure to this pressure, by increasing the pressure, I'm actually decreasing the volume. So that's what we have going on. This would be another isotherm happening up here. You'd have another isotherm in here. And they're basically these 1/x graphs that you have actually happening. The other one that's kind of a neat one is this one. The pressure and the number of gas particles are actually directly related. This is Avogadro's law. So we get it, if you add more particles in there, you're going to increase the pressure, kind of a duh statement. But they put them all together and we end up with what's known as the ideal gas law, sometimes referred to as PIV-NERT. Basically, pressure times volume equals the number of moles times the ideal gas law constant times temperature. The ideal gas law constant we're going to use is 8.31 joules per mole Kelvin. And so when we start dealing with PIV-NERT and looking at that, anything on the same side is going to be an inverse relationship. Anything on opposite sides of the equal are direct relationships. You can also replace the number of moles with the fact that it's the number of molecules divided by Avogadro's number, and you get what I sometimes refer to as PIV-NICT. So this equation right there is another version that I've used that's called PIV-NICT, where N here is now the number of particles. So this is the number of atoms or molecules and things like that. And this K is another ideal gas law constant, but this one's a little bit different. It's actually this 1.38 times 10 to the negative 23. I always think it's kind of neat that notice that it's just 8.31 divided by Avogadro's number, but what it did is it flipped the number. So 8.31 became 1.38, and then instead of 10 to the positive 23, it's 10 to the negative 23. The advantage here is you're not dealing with the mole, you're dealing with actual particles, so you get the joules per Kelvin that helps us. So we're going to use a little bit of both of those as we get some stuff out. So let's try one more example here. We've got oxygen in the lungs. We know they're little tiny sacs of air. Let's assume that they're under a pressure of 1 times 10 to the 5th Pascal. So they're about air pressure, normal air pressure from the blood. These sacs are called alveoli. The average radius is 0.125 millimeters, and the air inside is 14% oxygen. That's basically what air is. Assuming that the air behaves as an ideal gas at 310 Kelvin, find the number of oxygen atom molecules in one of these sacs. So using this PIVNICT, because now we're dealing with number of molecules, the idea is we're going to try to see if we can find that. So if I rearrange this to solve, the number of particles would be the pressure times the volume over K times T. So the pressure is given to us. It's right up there. We're going to treat these sacs with a radius of 0.125. So basically, we're going to treat these sacs like they're little spheres. So the volume of a sphere is 4/3 pi r cubed. So we'll have to actually calculate that. K down here is just our ideal gas law constant, and then temperature is given to me right there. Putting it all together, we've got our pressure. Here's our 4/3 pi r cubed. Notice we changed it to meters. There's our volume, there's our K, there's our temperature, and this is the number of air particles in there. Air particles is what I'm going to write. And then what we can do is we can multiply by 0.14, which is 14%, and this is going to find the number of oxygen molecules. So a neat kind of application of the ideal gas law constant to figure out some things in the ideal gas law. That pretty much finishes things up. The only extra thing that I have is a lot of times we like to split the ideal gas law up into different laws. We have Boyle's law, Avogadro's law, Charles' law, Gay-Lussac's. This is part of your lab that you're working with, and one of the things that we'll also see in this chapter. Hope you enjoyed this edition of the Henstitute, and we'll have some more fun with moles and the ideal gas law this week.